Let's follow through with some consequences of the algebra we just did. And so we can note first consequence of what we just did is that if we know the two solutions y1 and y2 and we evaluate the Wronskian associated with y1 and y2 at some time t equal to t0, and that turns out to be non-zero, then as we just saw that we can solve the system of equations that we had written. And so therefore we can find unique C1 and C2, these constants, which provide a solution which is made up of weights C1 and C2 for the two solutions y1 and y2, which gives a solution to the initial value problem. So y satisfies the prescribed initial condition y0 and the slope initial condition that we have demonstrated. And so that's an important consequence. Now let's look at a later consequence, another consequence. Let's look at a second consequence of the result that we had established. And so if we know two solutions y1 and y2 of the differential equation, and at t equal to 0 we evaluate the Wronskian and find that this Wronskian is non-zero, then we can define a homogeneous solution which we are going to represent as y sub h in terms of arbitrary constants c1 and c2 multiplying the solutions we know y1 and y2, and the important result is that such a linear combination with arbitrary constants c1 and c2 includes all solutions to the homogeneous differential equation. Any solution to this differential equation can be represented in terms of two known solutions which satisfy this property that the Wronskian associated with them is non-zero at least at some position within the interval of interest. Then that provides a general solution. All solutions is equivalent to a general solution, and it's also called a fundamental solution, a solution which can be used to represent a solution to a specific problem we seek. Y equals this general solution, homogeneous solution, plus a particular solution. And why do we need a particular solution to solve the complete problem? Is because the complete problem might have some inhomogeneity, it might have some forcing, and so the particular solution will allow us to satisfy the forcing, and so together particular solution and the homogeneous solution will satisfy the full equation and all the initial conditions and inhomogeneities that have to be solved for. Furthermore, using the idea of Wronskian, we can discuss the notion of linear independence. Now the idea of linear independence of two functions is exactly the opposite of what we would call linear dependence. And so let's define what we mean by linear dependence, and linear independence is the exact opposite of it. So if we have some open interval I, which is defined between two limits here, alpha and beta, t lies within alpha and beta, then arbitrary functions f of t and g of t are said to be linearly dependent if we can find some constants k1 and k2 such that the product of k1 times f of t plus k2 times g of t is exactly equal to 0 for all times in this interval. So the sum, if it vanishes identically over all of this interval, then clearly the two functions are not linearly independent. We can construct one function in terms of the other function. K2 minus k2 over k1 would be the value of this function f in terms of g, and so they would be linearly dependent. So linear independence is when we cannot express the two functions in this way, and so one important result that follows is that if we evaluate the Wronskian associated with the two functions f and g, and we find that the Wronskian is non-zero, then we can assert that these two functions are linearly independent. They cannot be expressed linearly, one in terms of the other. And so this will be very useful in solving the differential equation.